Hello, Internet. Today's project is the first use of my newly installed automatic tool changer spindle. I say newly installed, but it's a project I've been working on for several months, and I finally have it all hooked up and ready to go, except for the automatic part. The software for automatic changing the tools has not yet been implemented. So what we're doing now is just the manual tool change feature. This is a new spindle from the Jianken electric motor company in China, which I purchased through Alibaba. It weighs about 17 pounds, which is about 8 pounds heavier than the previous 2.2 kilowatt spindle. This also is a 2.2 kilowatt spindle with a 80 millimeter diameter, same as my former non-ATC spindle. To help support the weight, I added these two constant force springs. Here is one on the right side, and there's another identical spring on the left side to help support the weight of the spindle. The spindle has several connectors, all of which I'm kind of unused to. These two are the cooling water input and output. Then we have sensor wires for detecting heat buildup in the spindle. And that signal is sent to a computer, an Arduino computer I have located in this 3D printed box. We'll see that later on as the project progresses. We have a pneumatic tube. This blue one is for activating the tool changing mechanism. We have a orange air line that comes in which blows off the taper on the tool holder to take off any dust that may be in it. We have a third pneumatic tube, which is this black one here, which is what they call an air seal, which blows continuously a light quantity of air to keep dust from getting in the spindle mechanism while it's operating. And we have a fourth pneumatic tube, which is this clear one, which is used to be activated for a few seconds after a tool change to ensure that the tool has been firmly inserted into the tool holding mechanism. Here is a close-up of the spindle nameplate. Here is the spindle shipping crate. It took about 14 days to get here from China. The cost of the spindle was about $1,300, plus about $600 for taxes and tariffs. The other smaller box is the box that the VFD came in. I had to make several modifications in existing systems of my CNC. This is the CNC controller box. The original controller is just this section here, which housed my G540 Gecko oriented control system. But in order to accommodate additional inputs and outputs that the ATC spindle required, I had to add additional electronics, which are housed in this new upper part. We'll see some pictures of its interior here. The Gecko G540 is still the heart of the CNC machine, but I added this UC300 ETH motion controller from CNC4PC to enable me to add additional input and outputs that could be controlled by the Mach 3 software. Here also is a generic breakout board that was added. And here is a 4 relay printed circuit board that was added to enable the control of the air solenoids that control air to the ATC spindle. These modifications are based on plans provided by Cronus Robotics, the designer of my KRMx02 machine. Here is the ribbon cable that connects the original Gecko G540 to the new UC300 ETH. This Ether port now provides connection to the computer that controls the machine. In addition to the new electronics, we also had to add all of this pneumatic control equipment. We have 3 pneumatic valves controlled by the Mach 3 controller, although one is controlled just by the VFD. We have some air cleaning and water separating equipment for the air supply. And we have a very simple bucket that contains cooling water and a pump for pumping the coolant to the spindle. This is all located on the back of the CNC. The new ATC spindle uses these ISO20 tool holders. Here's a tool holder with just a simple 1/4 inch rod mounted in it. The manual tool change routine is controlled by this 3D printed box with what looks like a toggle switch, but that actually is a 2-position momentary contact switch with an up position, which I'll explain in a minute, and a down position. When the switch is in the down position, that releases the tool holder from the spindle and activates the stream of air to clean off any dust on the tool holder. Then the new holder, or the new holder with the new tool, is inserted and the switch is released. And then finally the switch up position is depressed to activate the mechanism that confirms that the tool is firmly in position in the tool holder. I'll demonstrate that whole process now. Pressing the down button releases the tool. Pressing the down button inserts the new tool, and now its momentary up confirms that the tool has been fully seated in the tool holder. As I mentioned earlier, the project is not fully completed. The future stage of the project will include software which will allow the tool changer to move to specific locations where new tools are located, and then automatically exchange one tool for another using software. Here is a gang of the tool holders that I plan to use. These are 3D printed from a model available from Pawn CNC, and they will be used to hold the tool holders in that future implementation. Here is a completed ornament like the one we're making today. It's engraved on both sides. So we're going to have to work on the front first, then flip the ornaments to do this final engraving on the back. Here is material for 13 ornaments. It is 1/4 inch Baltic birch that has been pre-finished on both sides with water-based target varnish. Because it's so thin, just a 1/4 inch, and it's being held on the perimeter by several wooden clamps, that can't be certain that the material will be flat against the spoil board in the center where the clamp action isn't effective. So we're first going to drill several carefully placed holes in the material to use for hold down screws to make sure that the material is flat against the spoil board. This is important because there are a lot of engraving features of the ornament, and engraving is particularly sensitive to any errors in the Z height. Because the Z is so sensitive, I'm going to check it with a dial indicator mounted in the spindle. Easy to do with the manual tool change. Each of the ornament positions was within 4 1/1000ths of the same Z height, so I considered that adequate. And for good measure, I added another 5/1000ths on the Z offset just to make sure we had adequate depth for a good crisp engraving. Coming up on 1 hour and 3 minutes. We're nearing the completion of this first tool path for the 20-degree V-bit. We were making the stars, the pilot, the 14 complete. I'm going to remove the tool for the first pass. I'm going to install the 30-degree V-bit for the second tool path. And now we're starting the second tool path for the 30-degree V. Just a couple of short paths of each ornament for this. And another tool change, removing the 30-degree V-bit, and we're inserting a 1.5 millimeter end mill. And that completes the tool path for the 1.5 millimeter tool. Required 56 minutes, 37 seconds, and we got up to 94 degrees Fahrenheit. Okay, this is the final tool change for the front of the ornaments. We're going to remove the 1.5 millimeter end mill. We're going to put in a 1/8 inch compression end mill to do the final contour of the ornament, leaving tabs to hold the ornament in the workpiece. tool change for the project. We're inserting the 20-degree V-bit for the final engraving on the back side. The holding tabs will be removed with this flush trim bit in a router table.